Alright there, ladies and gents, let's get into key part 2. So I'm not entirely sure what color this was printed on, but this is the second homework series, or second homework in the series of 4 homeworks. So this one we want to solve for theta. So it took us a while to get these types of problems. In fact, we're just kind of now getting to them. But the idea is this is really still solved in the same way that a composite function is solved. It's going to do with a little bit more work kind of on the back end. And so it's kind of weird to see the sign of theta in here, especially if I'm asking you to solve for theta. And so there's a couple different ways you can approach this type of problem. One is you can just accept that we're trying to solve for sine of theta and just proceed forward like you would with any other algebra problem. The second thing is to treat this, like I said, like a composite function and just do a replacement. So let me explain what I mean. So let's just say I'm going to replace a with sine of theta. Okay. And so if I kind of make this or I kind of invent this substitution, which is totally fine to do mathematically speaking, what we could actually do is a direct replacement. And so we can rewrite this equation as 4 times a plus 8 equals 6. Now, if that's the equation we're solving, that's not such a bad equation. It kind of looks weird with the sign, but if I just realize sine just represents another kind of function, and I call that function a, what I'm really solving is 4 times a plus 8 equals 6. Now this is actually really straightforward and quick to solve. We can solve this just like we would a linear equation. So we have 4 times a equals negative 2. Of course, dividing by 4, we have a is equal to negative 1 half. Now, at this point, since we have a solved for, we can actually go back and resubstitute in our value. And so since a is actually sine of theta, what we did actually solve for was sine of theta. So sine of theta in this case is negative 1 half. And so at this point, we can either go to our unit circle because this equation is saying, well, for what value of theta is sine negative 1 half, or we can apply like the inverse if we feel comfortable doing that. And so a way to think about it, again, 2 different ways. One, you can just logically say, well, at this point, I need to go search for this theta value. Or we can continue trying to solve for theta. And so one way we can do that is to apply the inverse sign or the arc sign to both sides of the equation. So if I take the arc sign of the left-hand side, which is sine of theta, I can also take the arc sign of the right-hand side, which is inverse sine of negative 1 half. Okay? Now, knowing what you know about the inverse and the function, what we have left on the left-hand side is just theta. And on the right, we have to solve now inverse sine of negative 1 half. Now, this is what I was saying before. We could have just stopped right here and logically went to our unit circle and found that theta. Or we can apply this algebra step to get theta by itself. And we actually end up with the same kind of question. What is the sine value for what angle, theta, does a sine value carry negative 1 half? Now, either way, we're going to go to our unit circle, and we're looking for the sine value, which is a y, to be negative 1 half. And so, let's see, that's not going to happen because if we're on the upper hemisphere, the y values, the sine values are all positive, so we know the value is going to be down here. We're looking for the second value, so here's one answer right here. And so it looks like theta is going to have a negative 1 half value at 7 pi over 6. Or, let's see, 210 degrees. It's also going to happen right over here. We have the sine value of negative a half. And that's going to be at, let's see, 11 pi over 6. Or 330 degrees. Okay, and so let's flip this unit circle away. And so I recorded that thinking off screen. And so we actually have 2 answers for theta. We can have 7 pi over 6 or 210 degrees if you prefer degrees, or it could also be 11 pi over 6 or 330 degrees. So this just says solve for theta. It doesn't say represent all the answers for theta because we know we can always do the rotation thing, like it's going to happen every rotation. But this is, I think, sufficient for this work at this point. So let's leave it at that. So again, like just to review the work, you could have just straightforwardly got sine by itself and then try to figure out the value for theta. But that can be confusing to think of like trying to solve for a function that's kind of embedded into another function, another composite. And so we can do a quick replacement. So we just took away sine just momentarily and realized that the equation is a pretty easy algebra problem. And then bring back sine at the end and solve for that. Here we have a tricky variation, but again, we just have to think of this as like um, a sign within a sign, or kind of, a function within a function. And so we have the sine of this weird thing, theta over 3 plus pi over 3 is equal to the cosine of, again, theta over 3 plus pi over 3. Um, and so if we're kind of understanding what this is saying, we have sine of this weird thing equals cosine of this weird thing. I'm going to do a quick replacement here. Like I'm just going to call again a to be theta over 3 plus pi over 3. And I'm only doing this temporarily. I'm introducing the substitution just so hopefully we can get a better understanding what this problem is actually asking for, because it seems really weird, but it's not as complicated as it seems. And so I'm going to replace both these arguments with a. And so this is actually just sine of a equals cosine of a. Now you don't have to think about it this way, but again, I'm just trying to help gain an understanding. So I'm trying to find when sine is equal to cosine. Since both those arguments were the same, a is the same as a, so this is just literally saying when is sine the same as cosine. And so let's go to our unit circle because it happens a couple different places. So if I look at the sine and cosine values side by side, like none of these are the same, so definitely nothing in quadrant 2. But if we look over quadrant 1, they actually are the same right over here. Pi over 4, which I'm gonna keep within radians because the question was written in radians. And so at pi over 4, the sine and cosine values are the same. Now that happens again over here as well as a negatives, but again, we said same, we didn't say positive or negative. So it happens at 5 pi over 4. And so I'm going to go ahead and record that off screen here. It happens two different places, pi over 4 and 5 pi over 4. Okay, so that's when sine and cosine are the same value, these two guys right here. So let's go back to our other screen. And so this is when those are the same. Now this does not answer the question because I asked you to solve for theta in this case, but at least we set some parameters. We know that the angle we're looking for is 5 pi over 4. So the way this would look is that we can say two different things. Let me actually make a little more room. So we can say two different things. We can say the sine of pi over 4 is equal to the cosine of pi over 4. We can also say, let's check this in blue, or we can also say the sine of 5 pi over 4 is equal to the cosine of 5 pi over 4. Okay, a little messy there, sorry about that. And so this is going to actually help us solve for theta, because we just said alpha, or a here, is equal to this expression. But that expression also has to be equal to 5 pi over, pi over 4. Same thing with this. We said alpha is equal to this expression, and that expression has to be also equal, or could be equal to 5 pi over 4. Which means now we got to go down to some algebra. If this expression has to have the same value as pi over 4, I can then claim that pi over 4 has to be the same as theta over 3 plus pi over 3. So again, we're just setting things equal to one another. Alpha has to be pi over 4. It also has to be theta over 3 plus pi over 3. And then we can set up a similar equation on the right-hand side. 5 pi over 4 has to be equal to theta, or could be equal to theta over 3 plus pi over 3. And so now, since we need to solve for theta, we just actually have to start solving this equation. So let's do this one on the left first. So if I'm going to have a hope for solving for theta, I need to get theta by itself. So let's switch colors here. So I'm going to subtract pi over 3 from both sides first. And so we have pi over 4 minus pi over 3. That's equal to theta over 3. So I'll multiply by 3 in the last step. But first I had to add these fractions together. You do this by getting both these into like terms. And so pi over 4, pi over 3, well that's going to be the same as 3 pi over 12. And then pi over 3 should be the same thing as 4 pi over 12. 12. Okay, and so I'm multiplying top and bottom by 3 in that case to get 12 on the bottom, common denominator. I'm multiplying top and bottom of pi over 3 by 4 to get common denominator. So 3 pi over 12 minus 4 pi over 12 is equal to negative 1 pi, or negative pi over 12. Okay, and that's equal to theta over 3. Okay. So last thing to do is multiply top and bottom by 3. We're solving here. And so 3's cancel here. Negative 3 pi over 12 is equal to theta, which is the same thing as negative pi over 4. Okay, so same thing on this side. We're going to do some nice algebra solving here. Let's shrink that a little bit so we get a little more room. All right, so solving for theta, the first thing we're going to do is subtract pi over 3 on both sides. So we have 5 pi over 4 minus pi over 3 is equal to theta over 3. We need like terms again, so we'll multiply the left-hand fraction by 3 and this fraction by 4. And so we end up with 15 pi over 4 minus 4 pi over, 15 pi over 12 is equal to 4 pi over 12. And this whole thing is equal to theta over 3. So subtraction, 15 pi's minus 4 pi's will leave me with 11 pi over 12 equals to theta over 3. Now multiply both sides by 3 to get theta by itself. And we have 33 pi over 12. Now that's reducible. I can take 3 out of both terms, so we have 11 pi over 4. And those would be our two answers. So we negative pi over 4, 11 pi over 4. It's a little more complicated of a problem, but if you think about the majority of the work, it's algebra. The big idea here was that we have to understand the question is really saying when is sine equal to cosine, go to a unit circle to pull those values, and then in a weird way set these arguments equal to each other. Again, it's just composite work. It's just composite functions. We're kind of going backwards, solving the outside to get to the inside. But in the end, we're kind of separating this theta over 3 plus pi over 3 separate from the sine and cosine functions. It's a function within a function. All right. Here we have a straightforward, this is reviewed just like the last key. We have a straightforward function. We want f of g of x. And so let's write this out first. So f, let's change this color. Let's write g in purple, and let's keep x in black. So the f function is defined to be 4x minus 10. Okay. But once I insert g of x into the argument, into that guy right there, this function f that was 4x minus 10, instead of the x, I'll write this function for g, and g is defined to be x over 3 minus 5. Now luckily we're also given the value of x. In that case it's going to be x equals 10, and so this function should be 4. And instead of x it's going to be 10, because it's a substitution for x, divided by 3 minus 5. And so it's going to turn a little messy, but no big deal. Like, they're just numerical values. So let's see, we have 40 over 3, so we can do some distribution. Minus 20 minus 10. So 4 times 10 is 40. It's over 1, so 1 times 3 is 3. 4 times negative 5 is negative 20, and then the negative 10 just carries. And so negative 20 minus 10, of course, will just be negative 30. So we have 40 over 3 minus 30. Okay, so fractional work, let's turn that into a value of 3. So we have 40 over 3 minus 90 over 3. Because 90 divided by 3 would be 30. And so the whole thing would just be negative 50 thirds. All right. So let's use the Pythagorean theorem to find the value of x. This is a right triangle, so it totally applies. So we have a squared plus b squared equals c squared. Doing some replacements, we have x minus 2 squared up plus x plus 5, which is the bottom, squared up, equals c squared. Now we want to find the value, oh, let's back up, sorry. C squared is 10, so it'd be 10 squared. Now we want to find the value of x, which means we need to solve this guy. And so again, please don't fall into this weird kind of folly, the folly being that you think you can square root out these squares. You are adding these square terms together, so you could not do that. The only way to actually solve this out is to expand it. And what I mean by expand is realize that if I have x minus 2 quantity squared, that's the same thing as having x minus 2, x minus 2, x plus 5 quantity squared, x plus 5, x plus 5, and 10 squared is, of course, 100. Now, this is brute force algebra work, but you can do it. Let's go ahead and multiply these two binomials together. And so we have x squared minus 4x plus 4. Let's multiply these two binomials out. X squared plus 10x plus 25 equals 100. And so we need to start collecting some terms. We have x squared and x squared. So that'll be 2x squares. Negative 4 plus 10 would be plus 6x. And then 4 and 25 should be plus 29 equals 100. So we're not done yet. In fact, the problem is now just getting rolling. Now we have everything laid out. We need to start thinking about what strategies we would use to solve this. If this were me, I would actually just use completing the square. That tends to work really well. And so let's get this 29 over to the other side of the equation. So 100 minus 29 would be 71. 70, 80, 90 is 100. Now, this is weird because we have a 2 and a 6. We're used to just seeing x squared, so let's go ahead and divide everything by 2. So we just end up with x squared plus 3x equals 71 divided by 2 is kind of a weird number. Let's see, 35 and a half. Okay, so now we can complete the square. Please recall completing the square is really just a fancy process for finding a better c value, so I can reduce this into a squared binomial term. And so this will be x plus 1.5 squared. And if I take 1.5 squared, that's 2.25, which I'll add to both sides. So this will be 35.5 plus 2.25, which is weird, but again, I don't really care. Being weird is not a bad thing in math. So this will be 37.75. Okay, and so this will be x plus 1.5 squared. Now to solve this, we can square root now since everything is a single term. Okay, and so this will be x plus 1.5 equals plus or minus the square root of 37.5, 75, excuse me. Plus and minus, of course, because we're applying a square root value. Last step, subtract 1.5 from both sides. And so we have x is equal to negative 1.5 plus and minus the square root of 37.75. Which I don't have a calculator handy in front of me, but if you want to, you could run that square root value and find the two decimal numbers. But that's not something I'm interested in doing now because we just wanted to find a value for x, and that's how you would find the value for x. And so again, kind of in review of this problem, the Pythagorean theorem just set up a situation in the context of the problem that created a pretty, not a nasty quadratic, but not one that's super easy to handle. But it is just a quadratic, and so you can expand those binomial terms. Once they're expanded, you can collect like terms and then begin to operate some algebra on it, solving to find the value for x, using, in this particular case, completing the square, because completing the square solves any quadratic really efficiently. We have to do some simplification, moving things over, but in the end, we could complete the square and end up with that crazy decimal at the bottom. All right, so let's go to this problem. All right, so let's do some factoring. I told you this semester is going to be really algebra heavy, so we're just making sure our skills are up to par. So we got to factor this out. Hopefully you can notice a couple things. One, that we have coefficients that are all divisible by 3. And you can also notice every term has an x value. And so what we can do is pull those terms out in front of a distribution problem before we start to factor first. And so if we pull a 3 out of every term, and we also pull at least an x out of every term, the remaining quadratic would be x, because 3x times x is at 3x cubed. I'm sorry, x squared, excuse me. And that would be plus x, because 3x times x would be 3x squared. And then minus 12, because 3 times 12 is 36. X times nothing to multiply by just carries that x. And so we have this first term of x, I'm sorry, 3x. And then we have this quadratic that I think we can factor, because x times x is x squared. 4 times 3 is 12, and if we go plus 4 minus 3, that will be the plus 1x in the middle. And again, since it's not equal to anything we can't solve, we can just factor, so we can stop the problem at that point. Here we have a classic sum of cubes problem, because if we look at 27 and view that as 3 cubed, and of course x, and so this first term, if we view it as 3x cubed, and this one we view as 5 cubed, we can reveal our a to be 3x, and our b value to be 5, because please recall, if you have a cubic in the form of a cubed plus b cubed, that factors formulaically into a plus b times the quantity of a squared minus ab plus b squared. Now that's a last semester thing. We call that the sum of cubes formula for what it's worth, because we're literally summing cubes. And so we can recreate that down here. Okay, so our a value is 3x, so that's going to be our a value here. And so that'll give me 3x there. For our b value, which would be this guy, we have 5, so it's going to be a plus 5. Then we have a squared, so that'd be 3x squared. Now you got to square the whole 3x term, so 3 squared is 9, x squared is x, minus ab, so minus 15x, because we're multiplying the 3 and 5 together, so that'd be 15. And then b squared, which would be plus 25. Now we can stop the problem at this point, because again, we weren't asked to solve for anything but just to factor it. And once we have two things multiplied together, the first term and the second, we have successfully factored it. All right, so let's put our tricks to the test here. Lots of things going on, but again, I think we can attack the top and bottom discretely. And so if we look just at the top, the first thing I notice is that we have a 3, an 18, and a 24. To me, that screams that we can take those numbers out first, or at least common term factor out of 3. And so if I take a 3 out of every term, I'm left with x squared plus 6x plus 8, which I think I can factor. We'll see that in a second. On the bottom, here we have a 2, a 12, and a 16. But also at the same exact time, I have an x in every term, an x, x, and x. So if I take out a 2 out of every term and an x out of every term, 2x times x squared is 2x cubed, so this first term. 2x plus 6 will give me 12x squared, or 12x, excuse me, I've taken it out, 6x. And then 2 times 8, or 2x times 8, excuse me, would give me 16x. Now, before I go any farther, after this first factoring, I have an entire quadratic that's the same as the one on the bottom. And so these are actually canceled directly. So I can cancel the whole top with the whole bottom, and just leave me with 3 over 2x. And at that point, again, I can stop, because I just asked to simplify, and there's nothing more I can do with this problem without it being equal to anything. Okay, let's do a little ACT prep. So again, we're going to take the tactic like the last key that I made, where we could do a lot of guessing and checking, but I think the best course of action is to just go forward with the algebra, actually just get through it. So we have x over 2 plus y over 3. And so we're asked which of these equations will always have the same solutions or solutions as this equation. That's a really clever way to say which of these equations is the same as the one I just gave you. And so what we're trying to figure out is if we have this equation, which of these is the same exact one. Now, if you're guessing and checking, that's one thing. You could pick values for x and y, substitute them into all the values, and see which ones actually are equal. But I think for us, the best thing we can do is just multiply everything out. Um, if you notice, and this is probably the biggest kind of giveaway, on the right-hand side of the equation, we have x and y as fractions of 2 and 3, but nothing on the answer set has fractions. And so what they're trying to communicate to you, the ACT people, is that, hey, simplify that side of the equation. Now, if you didn't know this trick, this is a really easy way to add two fractions together without having to do like the find the common term and do all the multiplication baloney. This is just a shortcut for it, but it's a fast way, especially if you're on the ACT, you want to be fast. So here's how this goes. It's going to look like cross multiplication, but let me assure you this is not cross multiplication. Please don't think it is. It's just a shortcut to trying to think what the common denominator is. And here's how this procedure goes. Here's this little trick. So if you multiply these two numbers together, the top and the bottom, and that becomes your first term. Then multiply going the other way, so bottom of the first times top of the second. That would be 2y. Keep the addition in the middle the same, so it would be plus 2y. And then put that over multiplication of just the bottom term, so that would be 6. So that we've successfully added or multiplied the fractions together really quickly. It's a really nice trick, especially on a test like the ACT. And this would have been no different if you multiply like this fraction by 6 and this fraction, or this fraction by 3 and this fraction by 2 to get its common term as 6. You just kind of do it in one step. Either way, let's go ahead and bring down the left-hand side of our equation, 4x at y minus 1. And so we're pretty close, but again, if you look at our answer set, nothing actually has a fraction on the right-hand side. So we're going to have to get rid of this 6. But again, this is straight up Algebra 1 type of, like at this point, we're past the hard stuff. We're just trying to simplify Algebra 1 style. And so if we're dividing by 6, of course, we'll multiply both sides by 6. Don't forget, because it's a subtracted term, you're going to distribute. And so if we distribute the 6's over on the right-hand side cancel, and we're just left with 3x plus 2y, which is great because we have that on the right-hand side. But here we have to distribute again because we're subtracting 1. And so 6 times 4xy should be 24xy. Then 6 times negative 1 is minus 6. So that would actually, oh, here it is. So 24xy minus 6 is equal to 3x minus 2y. And so again, we talked through the problem, but again, just do the algebra. That'd be my advice in the ACT. Don't try to do any kind of, let's substitute in numbers or guess and check. Just do the algebra. All right. So last problem of this homework. What value of a is a solution to the inequality a minus x is greater than or equal to c, but is not a solution to the inequality a minus x is equal to c? Okay. So we have to, this one, all variably defined. It's not going to help to solve numbers or to substitute numbers. We just have to do some hard analysis. So we have a minus x is greater than or equal to c versus a minus x is greater than c. So we want to solve this one, but not solve this one. And so the question you should ask yourself is, what's the inherent difference between the two? Well, hopefully you picked up that all the values are the same, and so the only thing that's different is that the one that we want to solve can be equal, and the one that we don't want to solve has to be strictly greater than, which tells you that the only difference is one value for a that makes them equal. And so the answer to this question is going to be when a minus x is explicitly equal to c. Now we are trying to solve for a, and so really all we have to do is solve this equation. And so if we add x to both sides, the only solution where this is not going to work, where it's going to solve the left but not solve the right, is going to be when they're equal, and they're equal when a is equal to c plus x. And so when they're equal is no good for this guy, which is why we want to find when they are equal, and a is equal, or I'm sorry, where they're going to be equal when a is equal to c plus x, which is option D, right? And so, so sometimes in these ACT questions, you just got to jump into the messy algebra. Sometimes you have to give it a thought first before you try the algebra. But again, I hope you're noticing the theme for this semester is you have to recall this algebra really carefully, all right? So that's key 2. There's 2 more keys coming. Let's go ahead and wrap this one up.